Guys, this is Mubin. We are talking about cardiovascular system embryology. The lecture today, we are almost near the end of these lectures. The lecture today is about the partition of primordial ventricle or the development of interventricular septum and aorticopulmonary septum. Important topics, and also some of the pathologies are really important. The clinical considerations are important. So let's get right into it. What you'll see here is that on this side we'll talk about interventricular septal development. So this is a primordial common septum and common ventricle, and we'll see how the septum develops. Here we'll talk about the aorticopulmonary septum development. This is more of a 3D orientation that we need to understand, otherwise it's a simple thing. And finally we'll do the clinical considerations related to APS and related to IVS, which is the interventricular septal development. So let's start. So what happens is, in about 4th week of the time, end of 4th week, beginning of 5th week, the ventricle, primordial ventricle, was one simple chamber. Let's orient ourselves. What is happening is, in this chamber, atria are opening through the divided AV canal. Then the aorticopulmonary trunk is also opening here. So this is the bulbous cordus, and this is the truncus arteriosus. It's not aorticopulmonary trunk, it is a common trunk, bulbous cordus and truncus arteriosus. So imagine this, many students find this difficult to understand, but this is really simple. Imagine if you have a room, and on the top of a room there is a chimney. That chimney is the common trunk, and somehow the room is going to divide into two, and the chimney has to divide into two as well and connect to each room. So that is the orientation. Back or dorsally we have atria that are dividing into two. Ventrally we have ventricle, which is the room, which would also divide into two, and on the roof is the aorticopulmonary trunk or the truncus arteriosus and bulbous cordus, and that also would divide into two and then combine with right and left ventricles. So that is the structure here. So you can see this is the important part here, truncus arteriosus and bulbous cordus. Also remember, please note it down, as part of this development, the bulbous cordus will become incorporated into right and left ventricle. On the right side it will make the infundibulum of the right ventricle, on the left side it would make the vestibule of the left ventricle, but the smooth parts, the outflow tract smooth parts of the ventricles are what are the contribution by the bulbous cordus. Truncus arteriosus, on the other hand, will become divided into pulmonary artery and aorta and the pulmonary artery. Okay. So what happens is, about the 5th week, there is a ridge that is called interventricular septal ridge that develops in the floor of the primordial ventricle near the apex of the heart. It starts from near the apex of the heart. This ridge is in the floor. So now imagine, on this side will be the right ventricle, on that side will become the left ventricle, and the ridge will grow. So it is going to grow from the apex towards the AV canal. So here is the AV canal that has separated the atria from the ventricles, and here in the roof is the aorticopulmonary trunk. So this ridge has to now start growing towards that. So if you see here, that is what you're seeing. This is the interventricular septum. Here it was the interventricular ridge here. This is the aorticopulmonary trunk, also called the outflow tract, having truncus arteriosus and bulbous cordus in it. This is right atrium, this is left atrium, and the two dividing ventricles. This is AV canal, which has divided, and if you see here, this is also AV canal, this one, and it has divided by the AV cushions. Endocardial cushions have divided this canal. So if the cushion was here, I'll make that in green. This was a cushion here, and that has divided the canal into two, and also the fibrous ring is formed, and also the the two AV valves have been formed. On the left side, this is the bicuspid or mitral valve, and on the right side, this is the tricuspid valve. So now think about this IV septum here. That septum is growing and it has a concave edge. Now throughout the growth, this concave edge is the, you'll call this, so this is a shunt between the right and left atrium. So this is the interventricular foramen. Ideally it would close, but not right away. The things that are important from a medical point of view are, number one, this septum that is growing, the septum that is forming, that formed from the ventricle, is muscular. It is built by the muscular cells that are contributing from the ventricles. So it is the myocardial cells that are making the septum. So the interventricular septum has two pieces to it. One is the muscular part and the other one is the membranous part. So if I make that, I'll make that here. Interventricular septum, ultimately when it would finish developing, it would have a muscular part and then it will have a membranous part. So together these two things will fuse together to make one septum that separates the right and left ventricles. Membranous part, it is really important to understand, membranous part is contributed by a different set of cells, and the myocardial or muscular part of the septum is contributed by a different part of the cell. So right now what we're talking about is the muscular part of the septal development. Now how would the membranous part, this interventricular foramen will be closed by the membranous part. We have to see how that membranous part comes together. Many cell types and sources will give origin to it. So hopefully this much is clear. We're going to go here, and to understand the membranous part, we have to also understand the aorticopulmonary septum development, because that also contributes to the membranous part. So let me give you a hint before we go there. Look, this is the interventricular septum, right? Sorry, interventricular foramen. Here is the membranous part that will develop. Part of it will be developed by the endocardial cushion tissue here. Part of it will be developing by the aorticopulmonary trunk septum, aorticopulmonary septum, that would develop here. Part of that is going to be developing by the contribution of the muscular septum, and that also means neural crest cells, which are making the endocardial cushion, will contribute to it. Neural crest cells are also going to make aorticopulmonary septum. So neural crest cells contribute to this, myocardium contributes to this, and mesenchyme contributes to that. So that is how the membranous part will come together. That also means there are lots of chances for that membranous part not to form correctly, and we'll look at the clinical problems associated with that. So let's look at the aorticopulmonary septum. Aorticopulmonary septum is a septum that appears in the common trunk. This aorticopulmonary trunk, aorticopulmonary trunk, or you can also call it common outflow channel, or you can call it the outflow channel. So this is the outflow channel, the blood was coming out of it. This one channel is going to divide into right and left, sorry, not right and left, it's going to divide into aorta and pulmonary artery. So how does that happen? First of all, remember this, the neural crest cells migrate into this area and they make ridges. We call them bulbar ridges, and the so that is what the conal ridges, so, or truncal ridges. So here is the bulbus cordus, here is the truncus arteriosus. A ridge appears on both sides of this, and that ridge will go down like this. It makes a twist. Another ridge on the other side will go down like this, and then they will fuse. So the end result of that is that when this septum is formed, this septum takes a turn, and that turn causes the aorta and the pulmonary trunk to kind of twist around each other like this. So they were originally a straight tube, but the tube got separated. So let's say it is this way. So fuse this here, and then from here, so that is the tube. This is how it happens. Now, why does this happen? It happens because of the blood flow coming from the ventricles. The ventricular blood flow is coming in a way that shapes the septum and its development, and it becomes a spiral septum. It does a 180-degree turn. Then due to that, what happens is, if this was the right atrium, let's say this is the right ventricle, this is the left ventricle. The blood from the right ventricle goes through here and comes out of here, that is a pulmonary artery, and the blood from the left ventricle enters here and comes out of here, and that is the aorta. So that is how these two things will become twisted. So here as well, same thing, the right ventricle is now going through the, this is the pulmonary artery, and the left ventricle, I'll make it with blue, left ventricle's outflow will go like this and come out, and that is the aorta. Do this black thing over here to kind of create an overlap. So that is the structure, that is the aorticopulmonary trunk. So how does that form? Bulbar and conal ridges or truncal ridges appear in the valves of the bulbous cordus and truncus arteriosus. These ridges go in a spiral fashion, 180-degree spiral, plus the neural crest cells that have come in and mesenchymal cell, they grow and they make the septum between them. So this becomes a septum that has a 180-degree turn. At the end of that turn, when it is completed, the left ventricle now is connected to the atrium and the right ventricle is connected to the pulmonary artery. The other thing is this. So I said that we'll talk about the membranous part. As this septum comes down, so keep an eye here, we are going to make the membranous part over here. As the septum comes down, it continues downward inside the ventricles and makes the membranous, contributes to the membranous part of the interventricular septum. Meanwhile, I'm going to make it in blue, the AV cushions here, that tissue also contributes from almost the right side of the AV cushions some more tissue, and that makes the membranous part of the interventricular septum as well. And of course, the interventricular septum continues to grow as well, and that is how the membranous part comes together. So that is the formation of interventricular septum and the aorticopulmonary septum. Now let's go to the clinical considerations, what happens. So there are some very important embryological problems that we should be aware of. Let's handle the interventricular septal problems first. So that are the problems here. These are very simple. First one is core triloculary biatrium. So what that means is, it's a 3-chambered heart, core triloculary, but atriums are 2. So if I make the heart like this, there are 2 atriums but 1 ventricle. So right atrium, left atrium, and common primordial ventricle. So that is core triloculary biatrium. This is the failure of development of interventricular septum. Then we have muscular interventricular septal defects. So I'll go here to the muscular part. So when the muscular part is developing, it sometimes have gaps in it, it sometimes have holes in it. These holes cause the shunt from left to right, and that is the interventricular septal defects. Depends what is the severity of them, and based on that we'll see the clinical manifestations. If they are not too severe, sometimes it just can work out, and if they are severe, then there can be right side hypertrophy because of the shunting. Then patent or membranous IVS defect or patent interventricular foramen. That is a more dangerous problem. So now what is happening is, if I make the heart here, so this is atria, this is atria, this is the AV canal, and the ventricle are partially separated. They are not fully separated. So the interventricular foramen, this one from left to right, that foramen is still there. So this foramen does not close because the membranous part of the septum did not form. Why did that not form? Maybe the neural crest cell, there is a problem with the CNS development, that also would have a problem with the heart development. And what kind of problems would appear? The AV cushions that would make the AV canal, that can be abnormal. The AV tricuspid and mitral leaflets can be abnormal, plus membranous part of the interventricular septum can be abnormal. So any of those reasons, if the interventricular septum is not present, then what would happen is, during the lifetime there will be shunting from left to the right, blood would continue from the left ventricle to the right, due to which right ventricle would start hypertrophying. When it will hypertrophy, at the end of that time, there will be right to left shunting. When the right to left shunting would occur, then cyanosis can happen. So let's talk that in a little bit more detail. Okay, so continuing discussing this one. So what happens is this, please remember this is an important topic. So right atrium opens up into right ventricle, right atrium opens in right ventricle, then left atrium open in left ventricle, and then we have the aortic, so from here we've got an aorta, this is aorta, or my depiction of aorta, and from here we've gotten the pulmonary trunk, which I'll make here. It's not important to see those trunks here. What is important is this, that the interventricular septum, this is defective. So throughout the life of the baby, the blood will continue shunting from left side to the right side. When that shunting happens, there will be, so please write it down somewhere, there will be increased blood flow to the lungs. When the lung blood flow would increase, so let's say if the lungs are here, this is the lung and this is another lung. When the blood flow to the lungs increases, then tunica intima and tunica media of the pulmonary vessels will become thick and muscular. Because of that, so once that becomes thick and muscular, if this was the artery, so let's say this was the artery, when it would become muscular and thicker, tunica media and intima, then the lumen of the artery would become narrow. So let's make the artery with a very narrow lumen. Now what has happened? What is the difference? Here the tunica media and intima have become so thick, the lumen is almost obliterated. Because of that, there will be increased pulmonary vascular resistance, or pulmonary hypertension would occur. That would create back pressure. That back pressure would cause right atrial hypertrophy, because now right atrium is pumping against higher resistance. Finally, the right ventricle, I was meaning right ventricle, not right atrium. Right ventricle will become so hypertrophied that it would create a shunt from right to left. But that would happen later in the life, like 10 years, 11 years old. So this, once we get the shunt from right to left, the venous blood from right side would start going to the left side, and that would cause cyanosis. So this is called Eisen-Menger complex. This is called Eisen-Menger complex, E-I-S-E-N, Eisen-Menger or Menger complex, and this is called, this will make blue baby, blue kid instead of the blue baby. Blue babies are blue or cyanotic after the birth. Here there is a baby who was fine for many years and then started becoming cyanotic or blue. So you have to be able to differentiate it. That is the Eisenmenger complex here, and the reason for that is that the shunt was left to right first and then it became right to left, and there is pulmonary hypertension with the right ventricular hypertrophy with the cyanosis. So that is the Eisenmenger complex, and this can happen in many other reasons, but at the end of the day there has to be interventricular septal defect. Alright, so now let's come to the aorticopulmonary trunk problems. So what can we get? We can get patent truncus arteriosus. It's simple. This is the truncus arteriosus and bulbus cordus. This is the common trunk. If the aorticopulmonary trunk, aorticopulmonary, not trunk, but aorticopulmonary septum does not develop, then the trunk would stay as one outlet, so it would look like this, a common outlet, and that is the patent truncus arteriosus. Now the problem with the patent truncus arteriosus is this. Here is the truncus arteriosus that has pulmonary vasculature and aorta, but it is patent here, it is not separated, right? So, and this is the ventricles. Ventricles are divided, but there is always a ventricular septal defect. Why is there always a ventricular septal defect? VSD, can you tell me? Right atrium. This is the patent truncus arteriosus. There is always a ventricular septal defect because aorticopulmonary septum contributes to the membranous interventricular septum. And if the aorticopulmonary septum is not forming, then that part of the membranous ventricular septum would also not form, and so there always will be a ventricular septal defect, always. And so due to that, as you can see, there will be shunting of left to the right. Second is that the blood will mix here in the ventricles and will go to body and to the pulmonary trunk in a mixture. So there will be cyanosis. So that is the patent truncus arteriosus. The second one is the transposition of the great arteries. This one is interesting, and depending upon the severity of it, it may or may not be compatible with life. So let's look at it. Not severity, but depending upon the other problems associated with it. So let me show you. This is aorta. This is aorta. This is pulmonary trunk. And what you're seeing here is pulmonary trunk is connected with the left ventricle and the aorta is connected with the right ventricle. This is right atrium, this is left atrium. So what is now going to happen is that the blood is coming in, venous blood through the superior inferior vena cava to the right heart, right atrium, from there to the right ventricle, all good so far, but then instead of going to the lungs, it is going to go to the body through the aorta. Would that work? No, body is going to get cyanotic blood or deoxygenated blood. On the other hand, the lungs will send the blood back through the left atrium into the left ventricle, and from there it would go back to the pulmonary veins and back to the lungs. So these have become two separate channels. Lungs and the left heart have become short-circuited, and body and the right heart have become short-circuited. So now the question is it compatible with the life? Depends upon the severity. If there are septal defects, for example, if there is atrial septal defect and there is ventricular septal defect, then the baby can be okay for some time. However, if there is no septal defects or there is very minor septal defects, then this is not a compatible situation, and as soon as the baby is born, one has to perform, the surgeons have to perform the atrial septoplasty. They have to actually surgically create a hole in the atrial septum so that there is left to right shunt and right to left shunt. So that is how that shunt will be produced. that would give baby a chance to continue living while the surgeons figure out that how to correct this situation permanently. So that is the transposition of the great arteries. It may or may not be compatible with life depending upon severity and the other accompanying defects. It has to have at least interatrial septal defect. Alright, then Tetralogy of Fallot, very common one, very commonly asked in the USMLE as well. It is simple. Tetralogy means there are 4 things, and Fallot was the doctor who found it and created the problem for us. So let's see. 4 things are here, and you can remember that with the mnemonic prove. So it's very simple. What happens is, so this is right atrium. Right atrium opens up into the right ventricle. Right ventricle opens into a very narrow pulmonary trunk. Now what is this problem? Remember, we are talking about the aorticopulmonary septum. So here the aorticopulmonary septum did not divide this common trunk correctly. So the pulmonary trunk is very narrow and aortic trunk is big. Now if aortic trunk is big, remember where the pulmonary trunk was? Pulmonary trunk was connected to the right ventricle. If it is narrow, the rest is aorta. That means aorta is also opening on the right ventricle. So aorta now opens on the left ventricle, that is where it had to open, but it has taken part of the pulmonary trunk as well, and that part is opening on the right ventricle. So now that means aorta here, if this is the left ventricle, then aorta now opens in the left ventricle and also on the right ventricle. So this is aorta. And this is the pulmonary trunk. So this is aorta. Aorta, pulmonary trunk. So now what are you seeing? What you're seeing is, clean it up a little bit. Now what you're seeing is a narrow pulmonary trunk or stenosed pulmonary trunk, a straddling aorta, straddle mean it is going out of its way as well, or overriding where? Overriding both ventricles, right ventricle and left. And then as that is happening, what's happening here? The right ventricle is now pumping blood in the aorta and it is pumping blood in the pulmonary trunk. Now pulmonary trunk is stenosed. That means right ventricle has to work more. That means right ventricle will become hypertrophied. So we got hypertrophied right ventricle. And finally, so hypertrophy, right ventricular hypertrophy, and finally because of this abnormality, it's a septal defect, that means the membranous interventricular septum would also have a defect, and so there is a VSD that is present, ventricular septal defect is present. So these are the 4 things that are seen. Start with the pulmonary stenosis and go logically. Pulmonary stenosis, aorticopulmonary trunk is displaced, pulmonary trunk is now smaller, that is pulmonary stenosis. That also means aorta will be now bigger, that is the second problem, overriding aorta, because it is now opening both in right atrium, right ventricle and left ventricle. Now because of the aorta on the right ventricle is going to pump into the aorta, plus it's going to pump against the narrowed pulmonary trunk, that would cause the hypertrophy of the right ventricle. So that is the third problem. And of course, because it is a problem with the aorticopulmonary trunk, the septum, that septum contributes to the membranous interventricular septum, there is going to be a problem with the ventricular septal defect as well. So that is what is the tetralogy of Fallot.